Today we're going to be talking about three-dimensional geometry. Don't worry, it's not as nearly as scary as it sounds. In fact, I think this is one of the easier units that we do. Although it does require like a little bit of like three-dimensional imagination, but not too much. But all the arithmetic you're using is just like you're plugging stuff into like basic geometry formulas and just like solving stuff. Like it's like math-wise, it's pretty simple. There's no complicated ideas going on, which is pretty rad, right? I would say it's tremendously similar or less complicated than what we just finished or got done doing, which is great. Okay. So here we're going to start here in just the first section. The first section is largely vocabulary. So let's just kind of run through a little bit of vocab. Instead of defining things in words, I'm just going to like give a picture and write a name for it, because I feel like that's going to be the most useful thing from a doing problem standpoint. Everybody cool? So here's a couple of 3D figures. The one on the left is called a cube. Great. What would we call the next one? This would be, rectangular solid. Or it's sometimes called a cuboid. I think that's more of a common European term for something like that, but I don't know how common it is over here, but it's, I would guess the odds are fair that half or so of us end up in like an IB Math Studies class next year. So there's that. Now, is a cube also considered a rectangular solid?
Yes.
Yes. Is a rectangular solid a cube? No. Okay. What's the next thing here? So it's a pyramid, but it's a type of pyramid. Yeah, we'd have to indicate the shape of the base. So this would be a square-based pyramid. Good. What's the last guy here? Yeah, wow. Somebody's got the notes open or something. This is called a triangular prism. Now, quick question, is a cuboid a prism? Yes. Is a rectangular solid a prism? Yes. Is a pyramid a prism? No. So what's the difference between those three things? That if I take a prism and I cut a cross-sectional area between that's parallel to the bases, that cross-section is the same shape as the base. It's congruent to the base. I should even say stronger than that, right? So like if I cut through the middle of the cube, the cross-section that I cut is going to look exactly the same as, the base, right? And in the cube, really, any of the parallel sides could be considered bases. Same thing in the rectangle, right? If I cut there, the cut that I'm going to make has the same shape as a base. Everybody agree with that? If I do that for the pyramid, is it going to be the same shape? Right? Even if I cut this way where it's parallel to the base, it'll be a different size square, right? Everybody can kind of see that? So not a prism. Here should be easy to see the triangles are the bases. So if you cut through there, you're going to get the cross section is going to be the same shape as the triangle base. Does that feel okay there? Okay, that's a page. Let's get some more pictures. This is fun, isn't it? Like, how much of a relief is this compared to the vector stuff we just got done doing?
I cannot. This is almost more stressful.
Well, the good news is that art doesn't count, right? At least in math class. I shouldn't say art doesn't count. Clearly art counts, but not when you're drawing your pictures in math class. All right. Let's take a look at these guys. What's that first picture? Yeah. The next one. Still another rectangular solid, right? Or you could call it a rectangular prism. Also wouldn't be incorrect. The third one? Yeah, so it's also rectangular prism, right? The difference is that somebody's looking at the notes at the same time. But notice that this one is slanted. So we're going to put in that extra descriptor. So in all reality, if I went back to the other rectangular solid, the second one there, I might want to add an extra descriptor onto that also. What descriptor would I want to put in there? I'd probably put right, since the sides form at a right angle to the base, as opposed to the oblique rectangular solid, where the sides are not, or the faces are not at a right angle to the base. Which one is usually going to be the easier one to work with? Yeah, the right angled ones, absolutely. How about this next guy? What's this? Nope, the fourth one, not the fifth one. That's another triangular prism. Notice that it looks a little bit different than the other one, but still a triangular prism. And you were right on this one that we call this guy a pentagonal prism. And here on the pentagonal prism, we might even be a little bit more particular, because if we look at that pentagon, it certainly appears to be a special kind of pentagon. Does anybody remember from back to your geometry days? This would be a regular pentagon. Do you remember what the term regular means? It means that all the side lengths are congruent and all the interior angle measures are congruent. Just as an aside. Feel okay still? Just kind of cruising through some vocab, right? Talking about stuffs. So here's another pyramid, right? Yeah, Sydney.
So why is the rectangular solid not a
You could still call it a cuboid. Sure. Rectangular solid and cuboid can be used interchangeably. You'd want to say oblique cuboid, but yeah, those two terms can be used interchangeably. So we got our pyramid here, but we might want to include some extra qualifiers here. So what other qualifiers could I attach to this pyramid? Square-based, okay, and then what else? Yeah, because really the height is at a right angle to the base. And just as a additional piece of vocab, this point here at the very tip of the pyramid has a special name. Does anybody remember this name? It's called the apex. So just kind of cruising through some vocab, right? Nothing complicated yet. I mean, other than like, hey, Mr. Kulik, this is like a poop ton of names. But do you think that on your test, Mr. Kulik's going to have like a matching thing with the names and the shapes? I just...
These are hard to draw. Can you?
No, I'm not going to ask you to draw them neither on a test.
Oh.
Get out of here. You just have to be able to, like, if I put the name of it in a story problem, you have to know what, like, oh, okay, like, this is what it looks like, so if I have to do something with it.
But you don't take points out for drawing.
No. As long as it's, like, reasonable. You've seen my drawings.
Yeah.
There's nothing special. Sydney, what's up? You're too busy answering all the questions to write everything down, huh? I'm just hassling you now. It's fun. It's like, why else would you get into education if you couldn't hassle students? You know? All right. Next four shapes. What's this first one? Sphere. What's the next one? Has a more specific name than half sphere. Hemisphere. Come on, global politics people. Right? What's the next third one here? Yeah. I think we've done that one already. And the last one here? A cone. Again, the tip of the cone, also called apex. FYI, cylinder could also be considered a, prism with a circular base, so a circular prism, sure. Everybody cool? Okay. Okay, time to review some basic area formulas. The area for a triangle is 1/2 base times height, or one half AB sine C. Right, we did that right at the beginning of the semester, correct? Okay. Area for a parallelogram. Yep. What's the sneaky part about the parallelogram, though? The height isn't a side length. So just keep that in mind. Notice that we didn't say length times width, which is tempting. How about a trapezoid? It's the average of the two bases times the height. Remember, in a trapezoid, the bases are the parallel pieces. And again, the height is not a side length. Usually, I guess you can have a trapezoid where the height is the side length, but usually isn't a side length. Usually is probably a bad word even to say there. Doesn't have to be a side length. Just like in a triangle, the height doesn't have to be a side length. Everybody's jogging some memories. Again, I don't expect you to have any of these things memorized. These would all be kind of given for you. Anybody remember the circumference of a circle? Yeah, buddy. The area of a circle? Yep. Good. So what about the curved surface of a cone? So the circle is flat, right? If we're talking about the three-dimensionality piece. The circle part is flat, even though I understand a circle is round, but like it's a flat surface, right? The rest of the cone, though, is all curved. Everybody agree with that? Okay. So this area, I guess I'll say CS for curved surface, is pi RL, where L is called the slant height. And it's basically the length of that side BC in the triangle BDC, where BD is the height of the triangle and DC is the radius of the circle. Or I should say the height of the cone, excuse me. And I always use the script L when I'm writing mine because, shoot, the lowercase letter L looks a heck of a lot like a number 1. And boy, that feels like a Mr. Kulik move to confuse the symbols that you've written down. So I use the script L to try to outsmart myself. Everybody feel okay with that? Okay. These were area formulas, right? Oh, what was basic area formula? Okay. So basic volume formulas. Look at us just cruising right along. So volume of a cone, does anybody remember that one? One-third area of the base times height. And what is the area of the base in a cone? Well, it's the area of a circle, so pi r squared. Notice I'm going to use the capital B for area of base and a lowercase b for just like a side length that we're calling the base. Everybody cool with that? How about the volume of a cylinder? Anybody remember that one? Area of the base times the height. In a cylinder, what's the area of the base going to be? Pi r squared. As a little aside, since we're talking about cylinders, if I want the area of the curved surface of a cylinder, so again, the circles at the bottom, if we think in 3 dimensions, are flat. The circles at the bottom and the top. But like the side of your can, you know, this part is all curved here, right? Everybody agree? What's that area going to be? Again, I'll use CS as curved surface. Yeah. So pi RH. Oops. 2 pi RH. Excuse me. Very good. So the volume for a sphere, does anybody remember that guy from your geometry days? It's a rough one. Four-thirds pi r cubed. Woof, Mr. Kulik. It's okay. Does anybody remember the surface area for this sphere? As long as we're talking spheres. Yeah. Okay. How about the volume for a pyramid? Still 1/3 area of the base times height. Here I'm not going to be more specific because you're going to have pyramids with lots of different shaped bases, right? It's not necessarily always a circle. In fact, it's never a circle because that's a cone. But it could be like a triangle or a square or a pentagon or a hexagon or all manner of terrible objects. So we won't be very specific there. We'll just use area of the base. How about for a prism? The volume for a prism. The volume for a prism. So just area of the base times height. Now there's one specific instance that we'd use a lot. So for rectangular solid, that's a specific kind of prism, right? The shape of the base for rectangular solid is a rectangle whose area of the base is length times width and then height. Okay. So that was our review of like shapes and basic formulas. Don't freak out about all the formulas you just saw. If you look at the review and you look at the formula page on the review, I think that's just about everything we talked about, plus some other stuff that we haven't might have yet. So take a look, but I think everything that we talked about here is on that review page or on that equation sheet. So memorization shouldn't be like a mega deal. You know what I mean? That's often a relief. Oops. Pressed the wrong button. There we go. Okay. The rest of what we're going to talk about here today, I'm going to just do with the PowerPoint because it's going to involve like drawing and shading and things that are beyond my skills as an artist. Just as an aside, I've put all of these PowerPoints on our My Notre Dame page. So if you look at the downloads box over here, we're going to have 3 PowerPoints, more PowerPoints for this chapter, and those are all in the download section if you want them to look at. Cool. Okay. But I'm going to just buzz through these guys because basically it allows me not to have to draw all these things in real time, which is kind of a hassle. So this might be a section which case drawing some of these pictures is not realistic for you guys when you're taking notes, and that's okay, right? All right. So the first section, we're going to be talking about finding the lengths of things inside of a 3-dimensional object. So to do this, what we're going to be relying on are finding right triangles within that shape. We call those triangles calculation triangles. So for example, if I have a right square pyramid, I could find the triangle ABC, which is a right triangle. And I could call that a calculation triangle, for example. Now, is that the only calculation triangle in that pyramid? Certainly not. It's just an example of one such calculation triangle. Okay? So I think probably the most challenging part of this entire chapter is just being able to look at a 3-dimensional picture and pull out the right calculation triangle that you need based on the information that you have, or the right combination of calculation triangles. Let's do a couple more. Okay, so sometimes some of these calculation triangles can be kind of unexpected or a little bit difficult to see. So for example, EAD, which is like half of a side of this cuboid, that's a right triangle. That's a good calculation triangle. That one should be easy to see. What's more difficult to see is that FGD is also a right triangle, even though it doesn't really look like it in the picture. So I know it's a right triangle because the side FG is perpendicular to the height GC, right? And the side GD is just in the same plane as GC is. So I know that that's actually a right angle right here. Can we kind of see that? Now it takes a little bit of imagination, which is why we're kind of going through and talking about some that are kind of tricky to see. But those would be the 2 calculation triangles that we've highlighted in this particular drawing. Are there more than these 2? Of course there are. Of course there are. But we're just kind of, we're just talking right now, just doing examples of pulling these things out. We haven't done any calculation, right? But right triangle calculations are going to be kind of what we'll do most of in this first section. So it's just going to be finding the correct right triangle that you need and then doing some like Pythagorean theorem or maybe sine, cosine, tangent, whatever kind of stuff on it. Here's another one, a triangular prism. Again, the pink triangle should be kind of easy to see that that's got to be a right triangle. CEF is just half of one rectangle, like one of these faces on my triangular prism. But the blue triangle here is also a calculation triangle. I know it is because this is a right prism, so BG should be perpendicular to BE. That the height of this triangular face is going to be perpendicular to this side, or edge, I guess we'd call that. It's an edge. Everybody's okay? Okay. So again, we're just kind of buzzing through looking at examples. Here's a case where the blue triangle is kind of the easy one to probably spot. We pointed that out earlier, right? As our first example of a calculation triangle. But this pink one is also also a right triangle, although it certainly doesn't look like it from the picture. But I know that the height is perpendicular to the base, so any edge that I draw that's in the same plane as the base is going to be at a right angle to that height EF. Oops. So angle F there is the right angle in EFA. Even though that looks like oblique from the picture, the issue is that you're taking a three-dimensional object and embedding it into a two-dimensional space like a sheet of paper. So you get some distortion from that, right? Have you ever noticed when you look at like a map on a sheet of paper, Greenland looks gigantic? Greenland's really not that big. It's a distortion from taking a three-dimensional object and trying to embed it in a two-dimensional space. There's actually different types of projections that you can do that don't distort Greenland that much. Or really, Europe looks a little bit bigger than it actually is area-wise. But you can talk about that in your geography class or whatever. I think it's the Mercator projection is what's commonly used. Anyways, this is totally off topics, excuse me. All right, so let's look at an example here. Here's a nice numeric example. It says a shoebox that's 32 centimeters long, 18 centimeters wide, and 11 centimeters high. And we want to calculate the length of the longest rod that'll fit inside the box. Okay, so my first order of business would be to kind of sketch a picture of what's going on. I'm going to then find any calculation triangle I might need. I'm going to redraw the calculation triangles aside from my picture and then do any solving that might need to be done. That's going to be typically my plan of attack for any one of these problems. Okay? So we draw a picture, figure out the triangles that we need to solve, draw those triangles on the side, solve that guy up. Cool? All right, let's go on. So here is my sketch. And the piece that I need, the longest rod that could fit in there is going to go from the top corner to the opposite bottom corner. Everybody's kind of feels like that's the obvious answer there, although you do need a little bit of like three-dimensional imagination to see that. But when you think about like an actual box, it's like, okay, yeah, diagonal from top to bottom, right? Should be pretty obvious. So the calculation triangle I need then is going to be this triangle like AGC, because it involves going from like the back corner, the top back corner to the bottom front corner. Everybody's cool with that? The problem is when I write in the measurements, I only know one piece in that triangle. All I know is GC. So I'm actually going to need a second triangle. I'm going to also need ACD because I need to get either AC or AG for that other calculation. Well, we're looking for AG, so I need AC in that pink triangle, right? So I'm going to find another calculation triangle that involves AC. the obvious choice here is ACD. So when I solve that, I get the square root of 1348. And that is going to give me enough to be able to solve the triangle ACG. Does that feel okay to everybody? Again, nothing that we've done is really complicated, right? The calculations here are really simple. We're just using the Pythagorean theorem and looking at a picture. Okay, so here's my other triangle. This was the square root of, what was it, 1348 is just as a decimal. And there we go. So now that I know two sides of that triangle ACG, I can solve for the third one. Piece of cake. Mr. Kulik, does it get harder than this? Not really. I mean, they're just ostensibly using the Pythagorean theorem and like finding side lengths of triangles. The worst case scenario is when maybe you have to do 2 or 3 triangles in conjunction. But like, big whoop, it just, fitting the information together. It's usually not too bad. We'll do another example here. So EABCD is a square-based right pyramid with sides of 12 centimeters and a height of 9.5 centimeters. We're going to calculate the length of EC, and then we're told an additional piece of information. Point M is marked halfway along one side of the base. We want to find the length of EM and talk about why the length of EC and EM are different. So here's my sketch. So the calculation triangle I've identified to find EC is going to be this one that involves EC. Again, you'll notice the issue right away is that I have only one side length. I need to find a second one. If we're looking for EC, I want to find a calculation triangle that involves FC. Anybody see one? FCD, good, that would be fine. That's a little bit trickier because you have 2 real variables there. I would probably, but that's fine. You could certainly do that, where you call this one X and this one X. Now, why do I know that this is a right triangle?
Because it's pretty similar to what it would be for EFC, because the height is perpendicular to the base.
Okay, this is a geometry pull. So the perpendiculars of what kind of shape are going to meet at a right angle? I believe rectangles. The perpendiculars of rectangles meet at right angles. Now the base here is a square, but a square is also a rectangle. So you know that like BC and AC are going to meet at a right angle. So surely the triangle that Luke described is a right triangle. But I had to pull a little bit of piece of geometry from that. What I think would probably be more or easier is that CDA is a right triangle. Everybody can see that one. Since it's a square, we know for sure it's a right triangle. And then I know that the diagonals of a parallelogram bisect each other, so FC is just half of AC. That would be the one that I think I would use. Yeah, that's what I said here. But what Luke described is also would also work. Again, oftentimes there's more than one calculation triangle you can use, particularly in a situation where you have squares. So here's my ADC. So I've solved for AC, and I know that FC is half of AC, so no big deal. Everybody's okay with that? Again, Luke, what you said would work also. Not a big deal. But, we're just talking, right? Just talking about maths and stuff. It's fun. Who's having a good time? Yeah, me too. I love not having to draw all this stuff because Lord knows, like, my art skills. Woof! Imagine trying to, like, get all these dotted lines in there and then highlight the thing that's the triangle that you're using and, like, woof. This is much nicer. Okay, so now that we have FC, we can then solve our triangle to find EC. So that was part A, right? This question had 3 parts to it, though. So we have EC. We also wanted to find the length of EM. So here's my calculation triangle I drew that involves EM. Everybody agree with that? Now, EF is fine. That's the height. We have that. But what's FM? It's got to be 6, right? Since I know that the side lengths are 12, I know that it's a right pyramid, so this point F is directly in the center of the square, which means it's 6 units from each side. Everybody's cool with that? So that was actually easy. You had to make the realization that, oh, sure, FM is just 6, but the calculation was really easy. And bingo, bango, bongo, there's my length of EM. Which one was bigger, do you remember? EC was bigger. So why do they have to be different? Why are they not the same length? This would be my best argument. If I take the triangle EMC, that involves both side lengths, correct? Everybody agree with that? Involves EM and EC. In the triangle EMC, that's a right triangle, correct? EC is the hypotenuse, which means it has to be bigger than EM. That's, I think, your best argument to make. Fairly simple argument, but like, you know. I think I said one is a slant edge and the other is like, you know, the height of a specific triangle, that they're just different measurements. But I like the argument I made for you guys better. You know, can't argue with that one. It's like these are 2 sides in a right triangle. One of them's hypotenuse, so it's got to be bigger than the other one. Done. Argument over. You win. Okay. I think we got a couple more examples, just kind of burning through this stuff. Again, has anything we've done been super complicated? Required a little bit of prior geometry knowledge and a little bit of like 3-dimensional imagination. But like, none of it was like super complicated though. We're just like doing stuff that hasn't required any of the difficult mathematics we've built out to this point. It's pretty straightforward. All right, so we got some cone here, and we're told the length of AB is 11.3, and the angle ABC is 53, so ABC. Calculate the radius of the cone. Okay, so here's my calculation triangle. How do I know that this calculation triangle I drew in shaded, how do I know that angle's 26.5? How do I know it was half? Because this is an important question, because when I do this, it's not always going to be half, right? If I go and I draw a triangle and I drop a perpendicular, like I've done here, it doesn't always split that angle in half. What's special about this triangle ABC? Not that D is a right angle.
Oh, it's a right angle?
It is not regular. The rate or the base is going to be a different length than the other two sides. But it's isosceles. Because this is an isosceles triangle, if I start at the apex, this perpendicular is actually a perpendicular bisector. So it splits the base in half. And it's an angle bisector. It splits that apex angle in half. So anytime you have a right cone, this will happen because the sides are the same on a right cone. If this was an oblique cone, goes out the window. You lose that possibility because now your triangle isn't isosceles because the side lengths are going to be different because one will be shorter than the other. Everybody cool as to why that was okay to divide that angle in half? Ooh, boy, I hit my mouse roll bar there. Everybody's cool? So what are we going to use to do this? We have an angle measure, side length, and we're looking for another side length inside a right triangle. SOHCAHTOA. Which one do I specifically want? Opposite over hypotenuse sine. Everybody cool? Again, easy right triangle trig stuff. This is way back to like the very beginning of first semester / geometry. You know, again, while the pictures might be complicated to kind of sort out and recall some of this prior geometry knowledge that at one point you did know, but again, it's been 2 years, so like, kind of goes. So far, so good? Okay. That's it for this section. We're going to stop here today. So at this point, I think you guys should be able to do like, let's see, what is it? It's like 1 through, not a lot, 8 or something, I think. Not even, 1 through 7. Now, just to be clear, moving forward, the rest of this is going to be involving, like, the next thing we'll do is finding angles inside of 3D things. And then talking about actually finding surface areas and volumes of stuff. Those are the last 2 sections. We'll do those 2 sections next time, so we'll finish up through 32. There's only 32 or 31 problems in the homework set, which is not so bad. There's no worksheet. That's nice. There's just a review. Cool. I'm going to tell you this. It's the one time only. Guaranteed. Next class, before break, what do you think is going to happen? We're going to finish the rest of the lecture in that class also. We're going to do the homework quiz before we leave to go for break. So make sure you've done 1 through 8 and you feel okay about that. We'll do a couple of questions before the homework quiz, but no. But we will have another partner one before the end of the semester, but they won't all be partner ones. This one will not be. You probably won't need any formulas past the Pythagorean theorem because we're not actually calculating areas and volumes of anything. We're just finding side lengths and stuff. So.